the second week of this our course Newtonian Mechanics with examples. So, we are discussing the Newton's laws of motion. So, this as you know that in the last lecture we covered our review of Newton's third law of motion and Newton's second law of motion. So, we are following a path which is somewhat unconventional. So, we are going backwards. So, first we discuss third law, then second law, and then we will go to the first law. The Newton's laws are very simple to state, but there are a lot of subtleties involved. So, that there are lot of conceptual misunderstanding among students. Hence, I quickly summarize and recap of what we discussed in the last lecture about the message of Newton's third law and second law. So, the learning from Newton's third law of motion is that the real, it sort of says that the real, what is a real physical interaction. So, the hallmark of a real physical interaction is that they always appear in pairs. So, the real force which is so you can contrast from something called fictitious force. So, some of you may have heard this term. So, this arises if you are measuring the forces and acceleration using a system of reference which is itself accelerating. So, we will not consider those kind of example in this course, but so this non-inertial frames are there. So, this is a difference between those kind of situations and the real physical force. So, the real physical force always appear in pairs which are equal in magnitude and opposite in direction. Now, I point out here that when we analyze the mechanics problem, there is an often a common misconception is to consider both part of this interaction in to analyze the mechanics problem. This is usually incorrect. So, you should usually focus on your system which and on the, if you define your system clearly, then you should consider only one side of this interaction as the force acting on the system. So, we will discuss this point in more concretely when we take examples, but let us now go to the Newton's second law. So, the message from Newton's second law, the first message is force is the agent that causes motion. So, it causes acceleration and not velocity. So, this is a great misconception, and I will come into in a few minutes why this misconception is so common. But this is what took the genius of Newton to realize that the effect of force is not to change position, but to change velocity. So, force causes change in velocity, which is acceleration. Now, here there is one point that I want to highlight, which is again a common misconception among students, is that acceleration, which is a change in velocity. So, change in velocity is a vector. Vector has both magnitude and direction, which means that it can change in two ways. The first way you can think of is that the velocity changes in magnitude keeping the direction fixed. For example, a body which is moving in a straight line and it is speeds up or slows down. So, for example, if you take something and drop it from the air, it follows a straight line in this case, but its speed is increasing if it going downwards. Similarly, if you throw something vertically upwards, then its speeds will decrease during its climb upwards without changing the direction. So, this is a common situation which is easy to understand, that the force the acceleration is due to the change in the magnitude of velocity. But there is another scenario in which the velocity, the magnitude of the velocity can remain same, but its direction can change, and if the direction changes, that means there must be an acceleration. So, a body moving in a circle, for example, even at constant speed has a non-zero acceleration, because if the body is moving in a circle, then its velocity is along the tangent and the direction, the tangent direction are continuously changing. So, there must be an acceleration. The second message from Newton's second law is that what matters is the net force, that is the what causes the effect, that is the causes acceleration is not the individual forces acting on the system, but the vector sum of the all the forces. So, for example, in this picture which we discussed in the last lecture as well. So, this is our system, let us say some particle, and on which there are 3 forces acting, but the particle will move in the direction of neither F1 nor F2 nor F3, but in the direction of the net or the total force, which is the vector sum of F1 plus F2 plus F3. So, this was stated in the momentum the impulse version of the Newton's second law, that the change in momentum is equal to the total force times the delta t, which is the net impulse on the system. The third message from Newton's second law is that the more mass means less acceleration, which means that the effect of this net force on an object is inversely proportional to its mass. So, this is evident from this equation. So, if we write the acceleration as F divided by m. So, you can see if you keep the same amount of force, but then if you increase the mass, then the acceleration caused will be less. Now, if we sort of combine all these 3 messages in a single picture. So, the first part is that this acceleration, which is the effect caused by the total force, and now if you replace this proportional to sign with an equality sign. Now, this equality sign itself is important, because the point here is that this means that the right hand side and the left hand side of this equation can be independently measured, and then this equality says that if you can determine the independently the f the left hand side and the acceleration and its mass on the right hand side, then they will be equal, where f represents the total force acting on the system, and this equality in both magnitude and direction. So, a consequence of this fact is that the acceleration of an object is always in the direction of the net force or the total force acting on the system. So, this equality is important because you can independently sort of measure the left hand side and right hand side, and it is Newton's second law which shows that they must be equal. Now, we go to Newton's first law of motion. So, here this is the least intuitive out of all the Newton's laws of motion. Why? So, consider this following example. Imagine that you are sitting on a rotating merry-go-round. So, merry-go-round is these toy horses which moves in a circle, and it is a favorite toy for kids, usually you encounter in a fair. So, if you all know that you will feel a force that is sort of trying to push you away radially outward direction. However, with respect to yourself, you are clearly at rest, you are not moving, that is your acceleration is 0. So, apparently this is a situation where you can feel a force, but there is but it does not causes an acceleration. So, does it contradict Newton's second law? So, this is the question which, to answer this question, we need another independent law which is the Newton's first law of motion. So, the question is that under what condition can we apply Newton's second law, and to answer this question you need an experimental test, and this experimental test is Newton's first law of motion. So, let me describe the test in steps. So, the first step 1, you prepare an isolated test body on which no force acts. So, this is the special situation, no force is acting on an object on your system. Then the second part is to observe its motion. Now, the test says that if such a body continues to move at constant velocity when no force is acting on the body, then you can, that is in a straight line at constant speed, which is same as saying constant velocity. So, if you observe this, then this is the condition in which you can apply Newton's second law of motion. So, let me it may sound a little bit confusing, so difficult to digest. So, let us go through it slowly. First is an isolated test body. Now, this part is very difficult, and this is the reason why Newton's first law is very counterintuitive to our daily experience. Why? Because we the humans on this earth, we are immersed in an environment where there is always two forces present. The first force is the gravitational force, our weight due to the attraction by the earth, and the second is that there is always some sort of friction. So, for example, we are immersed in the air, surrounded by air, the atmosphere. So, we are continuous, when we move through the air, we feel the drag force by the air. Sometimes we are in the water. So, when we move or swim through the water, we feel the drag force due to the water. We walk on ground, then we are in contact with some surface, and we experience friction. So, these two forces are always present in our environment, and our daily experience and physical intuitions are heavily biased as a result. So, the isolated test body means to remove all the forces. So, that means you have to consider a situation where you must remove the gravitational force as well as friction. Now, how to do that? Now, here is a beautiful the first one is actually removing gravity or switching off gravity is actually easy. This is a beautiful example illustration of the concept that force is a vector. So, all you need to do to remove the effect of gravity is to consider the motion of the test body in a direction which is perpendicular to the gravity. So, as you know that gravity is the direction that sets the vertical direction, because it is towards the center of the earth, and this is the direction we usually call the vertical direction. So, if you consider a direction which is the perpendicular to the vertical direction, that is the horizontal direction, then gravity has no component on the horizontal direction. So, there is no force of gravity if the test body moves in a horizontal direction. This is the easy part, and this is a beautiful illustration of the concept of dot product. So, this we have discussed in the first week of this course. So, if you know the force, then a force does not have any component in its perpendicular direction. So, now you have removed gravity. So, this is an easy part. What is difficult and challenging is to remove the friction and all sorts of contact forces. So, to do that you have to make sure that the test body does not touch any other body. So, no contact. This is a bit difficult to achieve in experiment. But suppose you can do that. So, the closest approximation of this kind of system is what is which is achieved in laboratory is usually demonstrated by something called a linear air track. So, here is a picture of such a system. So, it is nothing. So, note that there is a horizontal track which is this silver white path. So, this is a track on which there are pinpoints. So, through this there are jet of air coming through these pin nozzles, and this is the slider. So, it can, so because of these air jets coming up, it is not in contact with the track itself, but it is floating in the air, and then it can move in the along the track in the horizontal direction. So, this is a simple system in which you can sort of approximately turn off all the frictions, the gravity, and so you can sort of generate a condition in which no force is acting on your test body. So, I have put a couple of YouTube links where a video demonstration of the motion of the slider on the linear air track is shown. The first one is taken from a demonstration in IIT Kanpur, and the second one from a more detailed version of explaining what is this linear air track and how to use that to experimentally verify Newton's second law is from IISER Kolkata. Now, the second point is that now you have a concrete example of a test system. Now, you have to observe its motion. Now, what do you mean by observing the motion? It means you need to use a reference frame to measure the motion, the position, velocity, acceleration, etc. Now, what is a reference frame? A reference frame is not, very simply speaking, is nothing but a origin and a set of coordinate axes drawn from that origin and a clock. So, for example, in this picture this is the origin from which we have taken a set of coordinate system. So, these are Cartesian coordinate system. So, at this point it is does not matter which one is x, y, z, and you must have a clock on this. So, this is a clock to measure the time. So, this, now that you have this setup, then you can sort of observe the world and what is happening, the motion of this test body. So, you can measure the position vector, velocity, momentum, acceleration, force, torque, everything. So, this is called a reference system, a reference frame. So, this concept sometimes it is not used explicitly, but whenever we analyze any mechanics problem, we either explicitly or implicitly always working in a from a particular reference frame. So, here are some examples. For example, if you do not mention anything, that means usually you are working from the frame of earth, meaning the frame in which the earth is at rest. So, now if you observe earth from the space, from a satellite in space, as you see in some of the space related movies, that you will see that earth is actually moving with around the sun and also spinning around its own axis. So, that means if you attach such a coordinate system on with the earth, then that is also moving with the earth around the sun and rotating with the earth. So, such that frame is at rest with respect to the earth. So, this is the earth frame. Another common example is a frame of a train. So, imagine you are an observer sitting in a train which is moving at a constant speed on a straight railway track. So, another common example could be a frame of a lift which is falling freely toward the earth. Another example that we sort of discussed in just a while back is the frame fixed to a rotating merry-go-round. So, in which the observer who is sitting on the merry-go-round is at rest. So, these are the examples of possible reference frames. Now, the question is that in which of these frames the Newton's second law of motion you can use Newton's second law of motion to analyze problems. So, this is the test. In the candidate reference frame, observe, which means actually measure, how the isolated test body such as this linear air track moves. If so, isolated test body means no force acting on it. Under such condition, if it moves with a constant velocity, then we can apply Newton's second law of motion in that frame. So, this is the content of the first law of motion. Such a frame is called an inertial reference frame. So, Newton's first law basically says that inertial frames exist in nature. So, this is the physical meaning of first law, and sometimes you encounter in some textbooks that you can derive Newton's first law from Newton's second law by, let us say, putting the f is 0, you get the change in momentum is 0. So, it moves with a constant momentum or constant velocity, but that is not the point of first law. First law is actually a statement that when you have permission to use Newton's second law. So, this is why this is an independent law of motion. Now, note one thing, that the inertial frame is, there is no unique inertial frame. If you can identify one inertial frame, let us call that a base or reference inertial frame, then any reference frame moving with a constant velocity with respect to your chosen inertial reference frame is also an inertial reference frame, because so this is called the principle of relativity. So, now after we introduce and discuss the physical meaning and content of the Newton's laws of motion. So, now as we said that we want to the goal of our this course is to develop problem solving skill, the mechanics problem solving skill. Now, of course, if you want to develop problem solving skill in mechanics, the only way to do is to solve mechanics problems, to struggle with mechanics problems and come up with a solution. Only then you have the confidence that you can solve mechanics problems. There is no other shortcut. However, the point is that the number of possible problems in mechanics is basically infinite. So, you cannot definitely solve infinite number of problems. So, you have to do develop your skill in a smart way, and here I suggest some strategy for that. So, the strategy is to identify the different types of problems that is you typically encounter either in real life or in your mechanics textbook. Now, this is a disclaimer that so I have given you a sort of classification. So, this is based when the picture of the system that I have in mind are the system which can be modeled as a point particle. Now, we will encounter in real life and in this course situations where the system cannot be modeled by a point particle, you have to assume it is an extended object. In those cases, these are more complicated scenarios. These cases we can have more other types of problem, but for point particle we can think of 4 kind of situation. Some of these will of course are also, all of these 4 situations are of course valid for extended objects. So, here I write down to recall the Newton's second law. So, the version in which the total force divided by m gives you the acceleration of the object. So, the first situation is when the net force is 0. then your Newton's law, Newton's second law shows that the acceleration must be 0, which means the system moves with a constant velocity, which is Newton's first law. Now, a particular special case of interest is when the system is not moving at all. So, this is the so called statics example. So, this in this case we say that the system is in mechanical equilibrium and we are interested to know what are the conditions of mechanical equilibrium. Now, typically the problems, what kind of problems we encountered here. So, this gives you an equation. So, it says that if you add the total force you get 0. Now, typically one force is unknown. So, you can solve this equation. So, F total equal to 0. So, we shall see in more detail in the coming few lectures that you need an additional condition that the total torque is also equal to 0 in this case. So, this gives you two equations if you add the torque condition, torque balance. So, this is called the force balance and this is the torque balance. So, you have two equations. So, at most you can have two unknowns in unknown forces. Now, you get two equations, solve this equation to find the unknown. So, this is the typical problem. Now, here is a side remark again that how can a force be unknown. So, I want to draw your attention to two categories of common forces that you encounter in everyday life. So, the first category and typical example is the weight, that is the gravitational force due to the earth of, let us say you take a mass a particle of mass m, then its weight is always m times g, where g is the acceleration due to gravity and always towards the center of the earth, meaning that this force is always known both in magnitude as well as in direction, even without solving any problem. Now, contrast this example with another situation, for example, the contact forces between two surfaces. So, remember a typical block on a plane problem. So, for example, if I take this block on a surface of the notebook, then the contact force between the block and the notebook. Now, in general this contact force is unknown. So, as you know, typically what we do is that we resolve this into two components, one which is perpendicular to the surface and one which is parallel to the surface. So, the parallel to the surface is usually called the friction, but again this force is self adjusting and unknown in general. You cannot write down, you can sort of write it down symbolically as, let us say, n and f, n for the normal component, f for the friction, but you do not know what is the magnitude of n and what is the magnitude of friction. Usually you solve the force balance, the Newton's, you use the solve the Newton's second law, the force balance or torque balance, to determine the contact forces. So, these forces are basically called self adjusting and usually unknown, both in magnitude, direction, or in general in both. So, there are two kinds of forces, and interestingly this kind of contact force usually has a short range of interaction. That is, they are always they appear when you have two objects which are very either in contact or very close contact. Now, the second situation is a slightly more general version of this, that the total force is now non-zero, but the total force is given. It is let us say each force is acting on the particle is given. So, in this case our goal is to determine or compute the trajectory of the particle. How is the particle moving so for example, consider the example of a projectile motion. In this case, the force which is the force due to gravity is known. It may also have a force due to the drag force due to the air through which it is moving. So, that is also given. In this case, we want to know what is the path the trajectory the particle is taking, and how the position and velocity is changing with time. Now, this is the most straightforward application of Newton's laws. So, this is usually done in two steps. So, the first step is apply the second law in whatever form. So, for example, we can, let us say we use this first form in which we know the total force acting on the particle, and then apply Newton's law to compute its acceleration. So, this is known and this is unknown. Now, once we calculate the acceleration, then you can relate to velocity using the definition that acceleration is rate of change of velocity, and you can relate to the position with the definition that acceleration is second derivative of position with respect to time. Note that these are differential equations. So, this situation, this is now a mathematical problem of solving a second order differential equation. Now, as you know that if you want to get a unique solution out of a second order differential equation, you need to supply two constants of integration. So, these are, for example, can be thought of as the initial position and initial velocity at t equal to 0. So, if you know this, if you know where you are starting where you start to throw the projectile and what was its initial in which initial velocity, magnitude and direction of its initial velocity, then you can determine the subsequent trajectory of the projectile. So, this is a mathematical problem now. Now, there are two special cases of this situation. So, this case one in which this force is only a function of time. For example, some of you may have studied the oscillators, the motion of oscillators. So, let us say there is an oscillator. So, this is a common example in not only in mechanics, but also in electrical engineering and electronics communication engineering. So, suppose this oscillator is driven by a periodic force, which can be a AC signal or it could be a mechanical driving force. So, in this case usually this force is let us say it can be represented as some f naught sin omega t, where omega is the frequency of the force in some direction. So, in this case the force is only a function of time, and the other scenario in which the force is only a function of position. For example, the gravitational force, as you know, Newton's laws of gravitation shows that the force does not depend on time, but it depends on the distance between the two objects. And similarly, the spring force which says that the spring force is proportional to the extension of the stretch of the spring. So, it depends on the position of the end point of the spring. So, these two examples special cases I mentioned, because the mathematical tricks and tools to solve the differential equation are slightly different in these two special cases. Now, the situation 3 is the opposite, which means that the trajectory is given. So, you know the position, you know the velocity, you know the acceleration. So, acceleration is known. Now, you determine the forces acting on the particle. So, the force is now unknown. So, the most famous example of this sort is that given the orbit of Earth around the Sun, what is deduce the force between the Sun and the Earth. So, to deduce that this force is inverse squared, like proportional to the inverse square of the distance between Earth and the Sun, that is, it follows Newton's laws of gravitation. Now, this example is becoming more and more relevant in 21st century, because nowadays we launch many satellites in orbits near Earth and far away from Earth. So, we have access to lot of real time data about the position velocities of these satellites, and using these satellites or trajectories of these satellites, we can easily determine what are the forces acting on these satellites due to, for example, Earth or by Sun or etc. The fourth situation is probably the least common, but for the sake of completeness I mention this. So, this is a situation in which both the trajectory, that is the position, velocity and acceleration, as well as the total force are given. Now, you want to determine some properties of the particle, some properties of the system you study. So, one example that I can think of is from electromagnetic theory. In this case, suppose there is an electron which is moving in an electromagnetic field. So, it is experiencing the Lorentz force. So, in this field, under certain condition, you get a trajectory of the electron which is a circular circular trajectory. So, you can design different kinds of trajectories in which the electron will move by playing with the electric and magnetic field that you apply on the electron. And from this trajectory, so these trajectories are known, the applied electric field, magnetic fields are known. From this you can determine the charge to mass ratio, which is a fundamental physical constant of the electron. So, it gives you a very fundamental properties. This is also a standard first year BTech experiment in many places. So, now the reason I mentioned this is that now we have applied the first principle, that is the basic Newton's law. Just by looking at the Newton's law, we can think of these 4 types of situations that can arise. So, that now we have a handle, some idea about what kind of problems that we may encounter in mechanics. So, our next goal is to develop a analytical tool or thinking strategy to systematically attack the problems, for which our next goal is to develop how to use the free body diagram, which is our first technique that we shall use in this course to solve mechanics problem. This will be the subject of the next lecture. Thank you.